Hello, everyone. My name is Nailiang Xiang from Nagoya Institute of Technology in Japan. Today, I'm so happy to be able to attend this session and discuss with you about my research works. Here, I'm going to give you a presentation titled Ship Memory Alloy-Based Dampers for Seismic Retrofit of Continuous Bridges with Unequal Height Piers. This is the content of my presentation. First, I'd like to introduce the background of my research. As we all know, to accommodate the complex topography, bridges in mountainous areas are preferably built with unequal height piers, as we can see from these two pictures. Because of the unequal height, there usually exists a significant difference in the lateral stiffness among different piers. If the fixed bearings are used at the unequal piers, the peer-to-peer damage distribution, when subjected to a strong earthquake event, would be non-uniform or unbalanced, where it is clear to see that the shorter piers will become more vulnerable to shear or flexural failure than the taller ones. So AASHTO seismic design guidelines specify the design concept of balanced stiffness among different piers in a bridge to avoid any significant irregular seismic responses of the bridge. For example, the effective lateral stiffness ratio between any two piers within a bridge shall be no less than 0.5, and for two adjacent piers, it shall be no less than 0.75. The guidelines also recommend some possible methods for adjusting the relative stiffness among the unequal piers. For example, we can change the sizes or the reinforcement ratio of the pier columns, or we can use flexible devices like the isolation bearings or dampers at the shorter piers. Among all the stiffness adjusting measures, the one using flexible isolation devices would be very desirable, which could be used as an seismic retrofit option for such unequal height bridges. The common laminated rubber bearings can be adopted, but it should be noted that it is very difficult to have any desirable lateral stiffness through rubber bearings, since such bearings should also be used as vertical load supporting members, and the determination of their properties should also depend on the vertical load, not only the lateral load. Considering this, some other flexible dampers like the steel plate dampers can be used. These dampers work only in the horizontal directions with little effect on the vertical resistance, and thus their strength and stiffness can be designed as we want. So in addition to that, what if the emerging SMA dampers are used for such irregular bridges? So in this study, we are going to investigate the retrofit effectiveness of SMA dampers for the unequal height bridges. In the second part, the details and the finite element modeling of the prototype bridge will be described. Here, in the current study, a three-span continuous RC bridge was selected for study. The span length is uniform as 25 meters, but the height of these two piers, P1 and P2, varies, which are 6 meters and 10 meters respectively. For this unretrofitted bridge, fixed bearings are used at piers, and at end abutments, sliding bearings are used. The finite element model of the whole bridge was established using OpenSys, as we can see in the figure 2. In this study, we selected three retrofit devices: the rubber bearings, steel plate dampers, and SMA based keyboard dampers and implemented at the shorter P1 peer and compared their relative retrofit effectiveness. These are the analytical models of different retrofit devices. In the third part, the design of the SMA dampers for mitigating the seismic irregularity of unequal height bridges will be presented. So in the first place, we will look at the lateral pushover curves for the two unequal height piers. From the pushover results, it is obvious to see that the shorter piers shows a larger force capacity and stiffness, but a less deformation capacity than the taller piers. There exist big gaps between the shorter and taller piers in terms of the force and deformation capacities as well as the stiffness. Therefore, to fill such big gaps between these unequal height piers, some retrofit design objectives are proposed when designing the SMA dampers. First, we need to increase the deformation capacity at the shorter piers. Also, the uniform damage between the shorter and the taller piers should also be maintained following an earthquake. And most importantly, the use of SMA dampers should make the bridge system have a sufficient recentering capacity. So based on the proposed design objectives, the determination method of the required strength of SMA dampers was given. It should be noted that the implemented SMA dampers are in series with the shorter pier, but in parallel with the taller pier. The strength of the SMA dampers should not only avoid the premature failure of the shorter pier, but also ensure a restoring force for recentering the taller pier. As shown in this figure, it is desirable that the flat-shaped curve of the SMA dampers should locate just between the pushover curves of the shorter and the taller piers. The austenite to martensite force should be smaller than the force capacity of the shorter piers, and at the same time, the martensite to austenite force should be larger than the force of the taller piers. In this study, we use such kind of SMA and dampers with SMA cables to be implemented at the shorter piers, and this is the stress-strain relationship curve of a typical SMA. According to the design objectives, the SMA strengths can be determined like that. And to have a fair comparison, the steel dampers are also designed with the same force capacity as SMAs. Besides, the rubber bearings are designed based on the vertical load requirements. In this part, we will conduct the IDA-based seismic fragility analysis. And this is a set of selected real earthquake ground motions comprising 160 waves. So we chose a PGV as the intensity measure for scaling these ground motions. For each ground motion, the PGV was scaled from 10 to 200 at an interval of 10. At each scaling, we conducted 160 nonlinear time history analyses with the selected ground motions. For each bridge case, there were a total of 3,200 analyses to be carried out in the longitudinal direction of the bridge. So after obtaining the 160 IDA curves, we can calculate the probabilities of damage for the bridge at a given intensity measure. In this equation, the lowercase n. The lowercase n is the number of the ground motions with the peak responses exceeding a given damage state. The uppercase n denotes the total number of ground motions, and here it would be 160. After plotting all the fragility points, the fragility curves can be generated. The comparison of the retrofit effectiveness among different measures will be given with the fragility analysis result as shown in this part. These are the fragility curves in terms of the maximum pier displacement as a demand parameter. The damage limit state of pier yielding and failure were selected for illustration. As expected, without any retrofit measures, the shorter piers here is a P1. It's much more vulnerable than the vulnerable to the yielding of failure than the taller piers. So after retrofitted with these measures, including the SMA dampers, the fragility difference between the unequal piers could be effectively reduced. A relative balanced distribution of seismic damage could be achieved. So in addition to that, if we use the residue girder displacement as a demand parameter and investigate the relative fragilities of different bridge cases, it can be seen that the properly designed SMA dampers could effectively reduce the residue deformation of the bridge system. So in terms of the residue deformation-based fragilities, the SMA dampers show more effectiveness than the other two options, including the rubber bearings and the steel plate dampers. So to make it more understandable, the sample force displacement hysteresis for the longitudinal bridge systems were plotted, where the x-axis represents the girder displacement, while the y-axis denotes the sum of the base reactions of all the bridge piers. The amount of energy dissipation was also given in the graphs. We can see from these graphs that the flag-shaped hysteresis was very significant for the SMA retrofitted bridge system when the proposed design method was adopted. The energy dissipation through the hysteresis for the SMA systems was also very large when compared with the other cases with rubber bearings, for example. Here comes the conclusions. So based on the study results, the following conclusions can be reached. First, the unequal piers may show significant gaps in stiffness, strength, and deformation capacities, and that's why the irregular seismic responses are generated. Secondly, flexible devices can be well adjust the stiffness and deformation between the unequal bridges if properly designed. And if properly designed, they can also help achieve a uniform or balanced damage distribution among different piers. So SMA dampers as one kind of possible flexible devices can also balance the seismic responses between the shorter and taller piers. And at the same time, they show great effectiveness in reducing the residue deformations of the whole bridge system compared with other devices like the steel dampers or the rubber bearings. Okay, this is all my presentation. Thank you so much for your listening. Thanks.
Thank you, Dr. Jiang, for your nice presentation. So I see no questions. I have one just quick question for you since you have time for one question. Like, why did you choose PGV as your intensity measure for developing the fragility curve?
We actually, we tried many intensity measures, and we found that PGV shows a very the PGV shows a very good fit in characterizing the PSDM, the demand model, in creating the demand model than the other IMs like the PGA or any other IMs. So that's why we chose the PGV as a intensity measure in our study. Maybe for the other cases, it will be different, but in our case, the PGV is the best, I think.
Okay. Thank you.
Thank you.
So thank you, Dr. Xiang.